ratio test is one of the last really big ideas that we need to talk about before we start prepping for the AP exam. And again, I can't stress this enough. When I taught people through BC, and by the way, I've been up front, I did a horrible job prior to having a full class. I met with people maybe 3-4 days for an hour or so, each of those 3 or 4 days, and that was it. One of the things I always made sure I talked to people about was the ratio test, because the ratio test will come up multiple times. Usually it's a pretty big part of the series free response, okay? If you get lucky, you might just be asked about an alternating series, but you know, in general, it's probably gonna be some type of ratio test showing up in your free response. So I cannot stress how important this topic is. All right, so here's the concept with the ratio test. By the way, the ratio test can be used to prove a lot of the other types of problems we've looked at as well. But it's also one of your last resorts. And it tends to take place, it tends to be used when you have really, really complicated statements. And so, for example, let's say you list out terms of a series and you're looking at it and you're like, just doesn't exactly look like a geometric series to me. I'm not consistently multiplying by the same thing. So here's an example of that, okay? This is an alternating series, by the way. And so, you know, you're gonna basically alternate back and forth between negative and positive terms. We're cubing on the top and we're taking 3 to the nth power on the bottom. So you're starting out with -1/3. When you put 2 in there, you're going to get positive. 2 cubed is 8. 3 squared is 9. Then it's going to be negative the next time. It's going to be 27 over 3 to the third, which is 27, which is 1. So you can see here the terms are kind of growing. Wait a second, is that even? Oh, actually, yeah, that's kind of interesting too. So if you keep going, it looks like the terms are growing at first. You think, oh man, this is not going to converge. But notice if I go to a 4th value of n, 4 cubed is 64, okay? 3 to the 4th is 81, and we're back to having fractional values. So you can even get some weird things where it'll grow for a while, then it'll kind of decrease. Anyway, long story short here, this is clearly not geometric, all right? And so we haven't seen any of the other approaches here. I think if you just kind of use a little bit of common sense here, multiplying 3's infinitely many times compared to cubing a really big number, you know, that might also give you a little bit of insight. But again, you don't want to guess. You want to have a way to actually be able to show this. So first of all, the ratio test looks for something called absolute convergence. Okay, you'll notice this is an alternating series. A lot of alternating series are actually going to be pretty easy to show that they converge. And so what absolute convergence is going to do, absolute convergence will tell you if the absolute value of the series, in other words, if you had the series with positive terms, would it converge? And we know it's a little bit more common for an alternating series to converge than it is for a series that has all positive terms. So if you have a series that's absolutely convergence, the alternating series version of it would also converge, okay? So this is actually a little bit stronger type of convergence test than just looking at the alternating series test, even if you have an alternating series. All right, so the idea here is basically we would be asked, is this series absolutely convergent? And by the way, if the answer is no, it's still possible that the alternating series might be convergent. In that case, it's said to be conditionally convergent. In other words, the alternating version of the series is convergent, but the absolute value of this series is not convergent. That's called conditionally convergent. So anyway, a lot of terminology that's not super important to us right now, but over time we're going to see that come up, so I thought I'd at least mention that. Here's the concept, okay? If I have a geometric series, okay, say I had something like 9, 6, 4, and so on. Normally you could take the second term and divide by the first, okay, 6/9 is 2/3. Or you could take the third term and divide by the second, and you're going to get 4/6, which is 2/3. You can always take one term and divide by the one that comes before it, okay, to figure out what your geometric ratio is. Here's the concept. The ratio test basically says, all right, maybe our series isn't behaving like a geometric series for the first few values, but maybe if we go really far out, it'll start to behave more like a geometric series, okay? If we just go really, really far out. So what we do is we go infinitely far out, and we take the farthest out term and divide it by the term that came before it, okay? Technically, that would be that we're going to take the n plus 1th term and we're going to divide by the nth term, okay? And again, we're not going to look at the sign of this, okay? So we're going to take the absolute value of that ratio, okay? And just like in the geometric series test, you check to see if the absolute value of r is less than 1. Am I multiplying by something that is between -1 and +1? Same thing here. We're going to look to see if the absolute value of this ratio is less than 1 as I go out infinitely far. So I'm going to take the limit of the ratio of the n plus 1th term divided by the nth term as n approaches infinity. And basically that's saying, hey, if I go out really, really far, this series is going to behave kind of like a geometric series, okay? So it's not geometric, but it becomes more and more and more like a geometric series as you go farther out, okay? So that's the ratio test, okay? If the limit as n approaches infinity of the n plus 1st term divided by the nth term is less than 1, then your series converges, okay? If it's greater than 1, your series diverges. If it's equal to 1, it's inconclusive. You've got to use some other kind of test, all right? So let's take a look at this here. All right, so I'm going to look at the absolute value of the n plus 1th term divided by, and I'm going to write this down over here. We're looking at the absolute value of the n plus 1th term divided by the nth term is really what we're looking at here. Okay, so you're substituting in n plus 1 for each of these positions here. So you're taking -1 to the n plus 1. N becomes n plus 1 cubed. And that's over 3 to the n plus 1. Okay? So we're substituting n plus 1 in for each of the n values there. Okay? That's my top term. Okay? Now my bottom term is the nth term. Okay? That's just the original term of the series. Okay? -1 to the n over n cubed over 3 to the n. Now, if you look at a couple things here, I have n -1s, I have n plus 1 -1s. All of these are going to cancel all but one of these, and that's going to leave me with just a single -1 in the top. Okay? Now notice though, being multiplied by that, notice though, n is always positive. Everything here is always going to be positive. We're taking the absolute value of that whole thing, and that's going to knock out that 1 on top. So honestly, a lot of times when people do this, they'll really just take a look at that term right there. I don't want to say they toss out that -1, but because it's going to be an absolute value, essentially that's what's going to end up happening. All right, so I'm going to take out the absolute value here. We don't really need that anymore. We don't need that -1 there. Here's the key. Remember when you divide a fraction, that's the same thing as multiplying by the reciprocal. Okay, so this is a hideous fraction. Don't leave it like this. Okay, what I really want to do is I want to take n plus 1 cubed divided by 3 to the n plus 1, and I'm going to multiply by the reciprocal of the denominator. That's going to be 3 to the n over n cubed. Okay, and remember what we're really doing here. We're taking the n plus 1st term and we're dividing by the nth term. We're really trying to see, as you go really far out, is that ratio approaching something that's less than 1? If so, it's going to behave sort of like a geometric series. All right, so we just have to simplify this. We're really trying to take the limit of this as n approaches infinity. Okay, now here's what's so neat about this. If you look at this here, we're looking at the limit of this as n approaches infinity. I've got 3 to the n over 3 to the n plus 1. We can kind of group things in the numerator. We've got an n plus 1 cubed, okay, and we've got an n cubed. All right, notice we're trying to simplify this whole thing. n of these 3's will cancel n of those 3's. That'll leave us with just a single 3 in the denominator. So those all cancel, all but one of these cancel. We're just left with a 3 in the denominator. Okay, unfortunately I can't cancel something here because that would have to be FOILed out. You do not need to FOIL these out in most cases. Okay, so what I'm going to be doing is I'm going to be taking the limit of this thing as n approaches infinity. And by the way, if you don't like this, this 3 being here, that's a constant. Remember, you can factor a constant out of a limit. So I'm going to factor a 1 out of the top, and I'm going to factor a 3 out of the bottom. Okay, and that's going to give me something that looks like this. Okay, now think about this. This is going to be an n cubed numerator. We're going to have an n cubed denominator. Okay, the limit of this thing as n goes to infinity is going to be driven by those highest powers of n. Okay, the limit of this whole thing is just going to end up being 1 because you've got n cubed over n cubed. As you go really far out, it's just going to approach 1. So we've got 1/3 times a limit of 1. That limit is just going to equal 1/3. Okay, 1/3 is less than 1. Okay, so what this tells me is as I go really far out, this series is going to get closer and closer and closer to behaving like a geometric series with a ratio of 1/3. Okay, so again, it actually increased for a while, but then it started decreasing. And again, as you go infinitely far out, it gets more and more and more like a series with a ratio of 1/3, which would converge. Okay, so we can say actually that this converges absolutely. Okay, which just basically means that the positive version of this series, if it hadn't had a -1, will converge. Also, the alternating series will converge as well. Okay, so that's an example of the ratio test.